Hi, in this video we will learn about logarithmic functions. What is their definition, how their graph look like, what is their domain and range, and facts like that. Let us start recalling that the exponential functions, well, we know it is b to the power x. These guys have the graph as, let me just paste it here, I already have them ready. They have graphs of this form. And using the horizontal line test, we can see that, okay, so if I draw all these horizontal lines, they at most intersect one with this graph or none. Yes, that means at most. And also when b is between 0 and 1, the same story goes that, well, every horizontal line intersects with the graph at most once. That means that these guys are one-to-one function. Well, at b equal to 1, there's a big issue because you see, when I draw this horizontal line, since b equal to 0 gives us constant function that intersects the graph infinitely many times. So this piece, the only piece, only base for which the function b to the power x is not one-to-one. The other two, well, they are one-to-one. So this is the fact that the exponential functions b to the power x are one-to-one when b is, well, bigger than 0. We always take the base to be bigger than 0, but not equal to 1. And, well, if the function is one-to-one, you can look for its inverse. And yes, we can find the inverse. And actually, this is what is called logarithmic function definition. The inverse function of the exponential function f of x equals to b to the power x for all b's bigger than 0, not equal to 1, is called the logarithmic function with base b. The same base for the exponential comes here, and we have this, and we denote it by, so the inverse function of b to the power x, it's so important that we have a notation for that. Log b, that's the base at point x. So this is f inverse of x. This is just a notation. We use this notation. Well, as we know, the exponential means that, well, the inverse means that, in other words, we say x is a log of y base b is x if and only if b to the power x is equal to y. So it's exactly the inverse of exponential function. So if we're looking for log of y in the base b, we are looking for a number when you put in the power of b, you get x. You get y. So, okay, so this, let's do an example, some examples using just this property. This is the definition of log. Find the exact value. Find the exact values. First one is log of 81 base 3, log of 1 over 125 base 5, log of 0.5 base 2, and the last one is log of 10 base 0.01. Well, starting with for the first one, we are looking for a number when you put in the power of 3, you get 81. And with a simple computation, you see that 3 to the power 4 is 81. That means that the log of 81 base 3 is actually equal to 4. It's equal to the power. For 1 over 125 base 5, well, it's enough to see that 125 is 5 times 25, which is 5 to the power 3. So we have 1 over 5, 3, but we can write it as 5 to the power negative 3. The power which when you put it as the power of 5 gives us 125 is negative 3, and that's the log. For a 0.5, you see that this is the same thing as 1 over 2, but that is 2 to the power negative 1, so that is why we have negative 1 here. And when you look at 0.01, you see that, well, this is 1 over 100, and this gives us 10 to the power negative 2, yes? But we are looking for 10. How we can write 10 as the base, as some power of 0.01? Well, if you find negative 2 root of both sides, you get 10 is 0.01 to the power 1 over negative 2. So that is why we have negative 1 over 2 there. That is. Well, these are just examples. You have to be able to compute these kind of examples and evaluate log function in different, for different base, different numbers. Okay. So, then back to log itself, the domain and the range. Well, remember that the domain of the inverse function is the range of the original function. So here, domain of log x base b is actually range of b to the power x. But remember that b to the power x, look at the graph of b to the power x actually here. B to the power x for b is not equal to 1. They cover everything above the x-axis. So the range for that is 0, not including 0, to positive infinity. And the range of log x base b is domain of b to the power x, but we know that we can put any number we like to the power of b. That means that this whole thing is real line. So the range of log is real line, the whole real line, but the domain only accepts positive numbers. This is very important, and well, sometimes we need to be able to find, using this pattern, find the domain of a little bit more general function. For example, find the domain of f of x equals to log base 0.5 of x squared plus x minus 2. This is a logarithmic function base between 1 and 0, 0.5. And well, as we just mentioned, the values that we can put inside log or put as input for log, they must be positive. So in this case, x squared plus x minus 2 needs to be bigger than 0, not bigger than equal, just bigger than equal to 0. So we have to find all x's for which x squared plus x minus 2 is positive. Well, to solve an inequality, you need to find sign table. So sign table is what we do for these cases. And well, first need to solve it, set it equal to 0. This is quadratic. Either you solve it using quadratic formula, or you can see easily that two numbers which add up to 1 when you multiply get -2. These are +2 and -1. So x then +2 either is 0 or x minus 1 is equal to 0. The first one implies that x must be -2. The second one says x must be 1. Okay, the sign table now, x squared plus x minus 2. These are values of x from -infinity to 1, from -infinity to -2, and from 1 to +infinity. These are the values. We know that at these points we get 0. Well, find sample points here. For example, plug in 0 here, 0, -3, and you can plug in 2 here. For example, at 0, we have 0 squared plus 0 minus 2, which is -2. This is a negative sign. So here will be the whole negative. At 2, we have 2 squared plus 2 minus 2. These two cancel and we get 4, which is positive. So this gets positive. Plug in -3, you get another positive sign. So this is the sign table. But what we are interested in, where the function gives us positive numbers. So that is here and here. Do I need to include the 0 part? No, it doesn't have 0. It just says strictly bigger than 0. So that means that these for x's here or here, the expression x squared plus x minus 2 is going to be positive, and that log of those ones makes sense. So the domain of the function f is going to be -infinity up to -2, union 1 to +infinity. So that was about the domain and range. What else? We can also use the find the graph of this function. So graph of logarithmic functions. Logarithmic functions. Well, remember that the graph of inverse function for a function is obtained by finding the finding the reflection of the graph with respect to y equal to x. So in this case, first of all, we don't have this middle case. So we don't have this one. For the other ones, well, you have to find the reflection of the graph with respect to y equals to x. Y equals to x. And here we have y equals to x. Let me just put these ones down here, these ones down here, and let us just straighten this thing a little bit out. Okay, finding reflection with respect to x-axis as y equal to x. So here, for example, this point goes here, this goes there, this goes there, and this point here goes here, and as we go along there, it's just will go something down. So this is what we will get. For this other one, well, you do kind of the same things at this stage. At here, you stay the same. Here goes almost there, and here goes here. These are going down there like that, and so on. So you get something like something like this almost. So if you let me just erase these extra things here we had, you will see that, okay, these are the graphs of these log functions. I should have done a better job for this one. Let me just repeat this. Well, something like this. So these are both of them. You see that x equal to 0 is horizontal, vertical asymptote for these graphs. All of them passes through the point 1, 0. Before was 0, 1, now 1, 0. And for positive b, it is increasing. For negative, for b less than 1, it is decreasing. For b bigger than 1, it is increasing. Well, let us just then we have the basically this one, and then we can go ahead and draw a sketch graph of more logarithmic functions. For example, let me just do example, sketch the graph of function f of x equals to negative 3 log base 2 of x plus 1. Well, we have a base 2 here, so we can start with log base 2, this one, graph of this one, and then we'll do the transformation and get to this point. So let me start with this. So we have first 2 to the power x. Then we have to go the other one, log. This is log of base. Let me call this f0x. So we start from this. Then you see the x, we add 1 to x. So we switch x to x plus 1. So we get f at 1. Well, the first function is the previous function. You switch x to x plus 1, which gives us log of x plus 1 base 2. Then we multiply the whole function by 3, then we get f2 of x, which is 3 log 2x plus 1. And then the last step, we multiply the whole function by negative sign. This way we get the function that we have here, and that is negative 3 log of x plus 1 base 2. Okay, let us start with one function here. For b equal to 2, the graph of the function is something like this. And here is the point 1 and 0. When you switch x to x plus 1, what happens is that we have to do the horizontal shift 1 unit to the left. So it means that if I copy this thing, copy and then paste, I can get this here and just simply choose this point and shift it 1 unit to the left. Well, the point that before was 1, 0, now it will turn into 0, 0. Yes, we are shifting that 1 unit to the left, and that's the first step. The second step is that we multiply the function by 3 here, this one. This means that we have a vertical stretch by factor of 3, factor 3. So, so let me just then choose this one again and copy, then paste here. I will do it a little bit lower here, and then I will choose the function and try to stretch it 3. Everything is going to multiply by 3, so this is going to be this piece, this is going to be this piece. And well, the last one is multiply the whole function by negative. That's a reflection about x-axis. So reflection about x-axis, to run that thing, we need to choose this, copy, and then paste. We'll do it here again. Here. Okay, unfortunately I cannot apply the same tricks here, but I will do the reflection here with different line. I'll try to do my best. So it is going like that and like this. The other guy is gone. Almost. So this is basically, oops. This is basically what we have for this function. So the important thing is that you do try to see what is going on. By the way, the vertical asymptote also you can track. This is x equal to 0. Here we'll go to x equal to -1. A vertical asymptote, it won't change that, so this will be still the same, x equal to -1. And then the reflection about x-axis also gives us the same thing, so this will give us that was another example, and we did some work with the log functions. Let's just do one last thing, which is a definition. definition. Remember that when we were working with exponential function, the exponential function with base e were called the natural exponential function. Now here we have the same thing like with the base. When we fix base to be e, the logarithmic function with base e is called the natural logarithmic function. And it's so special that we have a notation for that, and we denote it by, instead of log base e, we denote it by ln or ln x. This is just a notation, log of x base e. And that is going to be called the natural logarithmic function. Well, this brings us to the end of this video. We had the definition. We used the definition to evaluate function. Then we had the domain. Based on the properties of inverse function, we found the domain. Then the graph of the function. We did some examples. And finally, we defined the natural logarithmic